So, over the last few weeks, let's just very briefly recapitulate. We saw that starting from Maxwell's equations, which were developed over a century previous to describe electric fields, magnetic fields, electric forces, magnetic forces, currents, charges. Like magic, Maxwell saw that out of these equations came electromagnetic waves traveling with the speed of light. He discovered that Maxwell's equations have solutions describing wiggling electric and magnetic fields propagating through vacuum, no charges, no currents, moving at the speed of light. Then what we saw most recently was we learned a little bit about how to make such waves. Maxwell first discovered that they existed as solutions to his equations, but then it was Hertz who was the first person to find a way of actually making such waves. And we now understand many, many ways of making such waves, and atoms do it all the time. That's when atoms emit light. That's atoms making electromagnetic waves. What I want to do now over the next few videos is I want to persuade you that light really is a wave, as described by Maxwell's equations. Now, we know that light involves energy traveling from here to there at the speed of light, but how do we really know that it really is electromagnetic waves and not some BB pellets of some sort? How do we know that light is not made of particles whipping along at the speed of light? How do we know that it really is electric fields undulating and magnetic fields undulating? And what we're going to do in the next little while is we're going to convince ourselves that light really is a wave using the phenomenon that is in many ways characteristic of waves, whether they be electromagnetic waves or water waves or sound waves. And that most characteristic phenomenon is called interference. So let's put up a slide illustrating interference. And let me walk you through this. So what we have here is a barrier with two slits or two openings. Now, this could be a picture of a breakwater in a harbor where the waves from the open ocean come in from the left, hit this breakwater, and if you have to have two holes in the breakwater so that boats can come in and out. And what that means is when the big ocean waves come in, the waves come through to some degree also. Or this could be a picture of light waves impinging on some sort of a screen, and that screen has two openings or two slits in it. Either way, if what's coming in from the left were particles, those particles will just fly through the slits, and nothing more to say. There's some particles flying in from the left. There's two openings in the barrier. The particles fly through the slits. What more is there to say? For waves, there's much more to say. So first of all, the first characteristic difference of waves is that when waves come through a slit like this, and the key thing actually is that this slit has to be similar in size to the wavelength of the waves, as you see it drawn in this picture, then the waves don't just come through straight as they would if they were particles, but they spread on the backside. And this is something that you're totally familiar with sound waves. If you imagine that you are standing on this side of a barrier and the barrier has two holes in it, and there's someone speaking on the far side, you don't have to line your head up precisely with where the holes are so that the little sound BB pellets come right through the opening and go straight into your ear. You do not have to do that at all. You stand on this side, you hear the person speaking, the sound comes through the hole, and as the sound comes through the hole, the sound waves spread. So you're totally familiar with this feature of waves. Now, but that's just the first part of the story. The second part of the story is what happens at a place like, say, here, for example, or here, or really anywhere in this region of the diagram. If I pick a spot here, this location is receiving waves from this opening and from this opening. It's getting waves from both the slits, from both the openings. And it's at a place like that where interference occurs. If what was coming through those openings were pellets, were BB pellets, were particles, then the intensity is just simply the sum of the intensity of BB pellets that you see at this spot is just the sum of the intensities that you see coming from the upper hole and the intensity that you see coming from the lower hole. With waves, that's not the case. It need not be the case. So let's see what happens with waves. So let's think about this spot in the middle right here, okay? And there's waves coming in from the left, waves coming in from the right. There's sort of a wave shown in blue coming in from the left and a wave shown in kind of orange coming in from the right. Now, what you should be imagining, I've simplified the diagram here, but you should be imagining that one of those waves is coming from one of the holes in the barrier and the other wave is coming from the other hole in the barrier. And we are sitting at some spot and we're asking what happens as these waves come together. And the key thing is that if these are waves, the way you answer that question is by adding vectors. Now, for us with electromagnetic waves, what we're going to be doing is adding the vectors representing the electric field and adding the vectors representing the magnetic field. We could do all of this for electric fields or magnetic fields. Let's talk about electric fields, but it's the same thing for the magnetic fields. So in an electromagnetic wave satisfying Maxwell's equations, what are we plotting in these diagrams? We're plotting the electric field. And the electric field is a vector. And when you add two vectors, sometimes if I add two vectors, 2 plus 2 becomes 4. But sometimes if I add two vectors, if they're pointing in opposite directions, 2 plus 2 becomes 0. And what you see is that in this setup, the way these waves are coming in, if you imagine continuing this wave, it's an electric field pointing downward. If I imagine continuing the blue wave, it's an electric field pointing upward. So in this middle region here, the electric fields are adding up anti-parallel, they're opposite to each other. So I have an upward electric field and a downward electric field. I add them like vectors, I get 0. So 2 plus 2 here is adding up and giving me 0, and that can never happen if what I have is particles. With particles, their intensities, the flux of particles from one side and the flux of particles from the other side just add. So here, if I look at electric fields on the left, 2 plus 2 is adding to 0. But now let's pick a different spot, okay? So maybe previously I was talking about, this exact spot. Now maybe we'll move to a slightly different spot. In this other spot, again, there's waves coming from the two slits, from the two openings. There's a blue wave coming in from the left and an orange wave coming in from the right. But this time, the phase relation is slightly different. So that this time in this middle region, the two waves from the two sides line up. And so at every point here, the electric field from the wave coming in from the left and the electric field from the wave coming in from the right are lined up. They're either both pointing up or they're both pointing down. So now when I add the vectors, when I use superposition, so notice, by the way, that way, way, way back at the beginning of 802, one of our fundamental features of the laws of nature encoded in Maxwell's equations was that electric fields add like vectors, the principle of superposition. And we're using that throughout what we're doing right now. So you add the electric fields like vectors, and what do you get? Well, here you get 2 plus 2 equals 4, because the electric fields are parallel to each other. When you add them, you get an electric field that's stronger. So 2 plus 2 is 4 in this case. So here, 2 plus 2 was 0. Here, 2 plus 2 is 4. So electromagnetic waves, by virtue of being waves, when waves from two slits or two sources arrive at the same point, at whatever the point we're talking about, those two waves can either interfere destructively, as on the left, or constructively, as on the right. And neither of these can ever happen with particles. In particular, destructive interference is particularly striking. The idea that you can have waves coming in from two from two spots, but what you see at the place where you're looking is no wave at all. That is a characteristic phenomenon that can happen with waves, but it cannot happen with particles. Now, before ending this video segment, I want to emphasize that I keep saying can happen with waves, but interference doesn't have to happen. So what are the conditions that you need to satisfy in order to get interference? There are actually two conditions, and I'm going to mention the second one first. So monochromaticity, that is a long word that is hard to say, but it's a simple idea. These two waves, in order for them to interfere, they have to have the same wavelength. The fact that in this region in the middle, they're perfectly canceling each other, that would not happen if one of them had a much shorter wavelength, or one of them was jaggedy and spiky, and the other one was nicely sinusoidal. They have to, the two waves have to have the same wavelength in order for them to cancel, or in order for them to add in the way that I showed here, to perfectly add or to perfectly cancel. So one requirement is that the waves we're talking about have to be monochromatic, single wavelength. And then the other condition is coherence. And the way to think about that is to think about what would happen as a function of time. So these pictures are drawn in a stationary fashion, but you have to imagine that the waves are moving. These waves are coming together here, and these waves right here, these waves are coming together here. Now, if the phase relation between the source of the waves from the left and the source of the waves from the right changes, then at one moment in time I might have the picture on the left, but if I stay at the same spot, wait a little bit later, the phase, the waves that were perfectly out of phase canceling destructively, they might, a little bit later in time, they might become in phase adding constructively. So if I want to be able to say that at this location right here, there is destructive interference, the waves are canceling, and that's true now and it'll be true later, that means that the phase relation of the waves from the two sides has to be the same. It has to be constant in time, and that's called coherence. So the two things I need in order to be able to describe interference in the way that I am is coherence. The sources have to maintain a constant phase with respect to each other, and monochromaticity. The two sources have to be monochromatic. They have to be emitting waves with a single wavelength, and the wavelength has to be the same from the two sides. If we have sources of waves with those two properties, then we can get interference. And in fact, one of the easiest ways of satisfying these conditions is the single source of waves sending light or sound or water waves through a barrier with two openings, the two-slit experiment. That is, in fact, one of the easiest ways of satisfying these conditions. And so on the downstream side of those two slits, we will indeed see interference.